Okay, so Andy Pitman here. This is going to be very quick, otherwise Ian doesn't get any time. Thanks to lots of people who contributed. Is that you don't want lots of time? And loads of other authors, those not listed here, are by accident of omission. Why is it? Which button do I press? The first is talk about Ming Yuan's work. Groundwater and cable. She's been working for quite a long time in trying to represent groundwater in cable. This is actually quite important. It changes the lower boundary condition of cable from free drainage to having moisture that in principle can either moisten the lower soil layer or in theory at least be accessible by roots. It's extremely simple. If you're an actual card-carrying hydrologist, you would go grey looking at the level of simplicity we're doing. But this is designed for global application. So we want it to work everywhere. And if you want it to work everywhere, it has to be simple. The groundwater parameterization has quite an impact. This is published in Earth System Dynamics. Adding groundwater improves the simulation of total water storage. That's in comparison to GRACE in particular. It improves the simulation relative to the free drainage parameterization. That's not a particularly high bar to cover, but it does seem to have benefits, in particular in periods when we're going into drought. This is the impact of groundwater during drought. The impact on evaporation is not insignificant. An extra 50 to 200 millimeters of evaporation occurring in drought. Most of that is via transpiration, which has thereby implications for the carbon balance. So groundwater has a temporal and regional specificity. It's most important where the groundwater is quite shallow, which is not exactly surprising. But what is a bit annoying is there is a coupling between roots and groundwater. Not necessarily roots into groundwater, but the way that groundwater moistens the lower soil layer opens up opportunities for roots to provide an evaporative flux during drought. So we get into this immediate nested problem that there is a coupling between the groundwater and the roots. This has feedbacks into the atmosphere. This is coupled simulations with WRF. Groundwater is cooling, maximum temperatures by up to 3 degrees during extreme heat events, which you can see on the right-hand side. Note the regional specificity here. It's particularly influential in those regions with forests. And the reason for that is the groundwater is deep enough that it doesn't necessarily moisten the landscape significantly underneath grasslands. You want the roots to be able to get down to where the groundwater is influencing the soil moisture. Stages new hydrology scheme. I hope this is right. The work that Ming Yuan's done is not just groundwater. It also adds better runoff generation processes, better representation of saturated and unsaturated soil moisture, pedo transfer function, and a range of other stuff. Implementing that into ACCESS might not be that easy because you need to be carrying some additional global fields, which is always frightening in the ACCESS space. In the WRF space, it's fine, it's running happily. The actual additional code has been implemented in an offline branch of cable and has, I think, Ramsey might freak at this statement, now being implemented at the head of the trunk. There is testing planned for this month, but on the right-hand side is a result from just one set of simulations, and it doesn't matter what the lines are. What matters is there is a line there for the head of the trunk, including groundwater. So I'm not saying it's ready to run in ACCESS ESM 2, but it runs in the trunk, which is a step forward. However, I'm nervous about this in terms of CMIP 7. Groundwater does seem to matter, but the equilibration of the groundwater depth has significant implications and needs to be woven in with vegetation parameterizations. you can have a very, very small error and you can equilibrate your groundwater much too near the surface or conversely much too deep, and that kicks the system reasonably hard. I don't know how we fix that problem because it's not likely there are no errors in the parameterization. So if you equilibrate too near the surface, you suppress changes to do with drying and you suppress the likelihood of extreme temperatures. Conversely, if you equilibrate too deep, you get too much tendency for extreme temperatures and probably a bigger kick to the system. And it's like soil carbon. What you equilibrate your soil carbon to strongly controls the change in the soil carbon as you warm the planet. The equilibration takes a long time. I can't remember if it's 50 years or 500 years, but it's still a long time. We are using the LIST system. We need that. I think we need that LIST system integrated into cable now. We need to be able to spin cable up for very long periods of time with and without nutrients, with and without groundwater, et cetera, and LIST provides a really neat system. And the sooner ACCESS-NRI solves all our problems with respect to this, the better. Other things that we've been working on, Manon Sabot worked for her PhD on plant hydraulics. I'm not going to go into any detail here, but this allows us to actually explicitly model when plants will wilt and die under moisture stress. This replaces some empirical functions that we use in cable, but are used in many other land surface schemes. The scheme only works for trees. It could be optimized to work for grasses, but that work would need to be done. It needs quite a lot of data, and it needs quite a lot of work. But I think it is the way forward. There are several land surface schemes around the world using this kind of an approach, optimizing how the vegetation responds to moisture stress and how hydraulic cost increases under moisture stress. I think it's probably bringing us up to date with a lot of ecophysiology work that's been done. I'd love to see it stable and operating in cable, particularly for landscapes that are semi-arid and drought-prone. I think it would help a lot, but I don't think it's ready, and it's certainly not ready for Siemens 7. The reason the plant hydraulics is really important is it lets you predict something really important, which is when trees die. If you can predict when trees die, you have quite an important feedback on things like fire risk, but also carbon, obviously. Mark DeCarl worked on this at length, has some nice papers in New Phytologist and Global Change Biology on the capability of actually simulating hydraulic stress and death of trees. I think this stuff offers a very nice link between land modelers and ecophysiology, and it offers that critical thing, the prediction of mortality. And one of the big things I think we need to move forward and deal with is that link between fire, carbon loss, and mortality. The other last thing I'm going to just touch on is work that Jana has been working on. She has been exploring the impact of lateral flow in the soil of soil moisture. She's running at very high resolution. This is again in WARF. It's not using cable because the capability to do lateral flowing cable hasn't been developed. She's finding quite significant impacts of lateral flow on latent heat flux. It's highly scale dependent. As you can see on the left-hand side is control, but then as you move towards the right, we have 1 kilometer, 4 kilometer, and 10 kilometer simulations, and you really start to see an impact at 1 kilometer. But note the change of the sign of the impact of lateral flow as you move from 10 kilometers where there's lots of blue to 1 kilometer where the blue is along the rivers and the rest of the landscape is brown. Lateral flow can change the sign of the latent heat flux, but all we need is our models running at 1 kilometer. And it implies that adding lateral flow might give you the wrong sign of the change if you're running at 10 kilometer, which is something that's going to have to be explored a lot more. There is no chance of getting this kind of stuff into cable for Siemens 7. I don't think we even want to, but it's the sorts of directions that we need to take for Siemens 8 when we're running our global models at a few kilometer resolutions, hopefully. So in terms of future directions, just a few things. I think most of you have heard many times now that as an atmospheric model increases its resolution from hundreds of kilometers to tens or fives of kilometers, in almost all parts of an atmospheric or indeed ocean model, less has to be parameterized. Life becomes simpler. At very high resolution, you don't have to worry about lots of stuff because it becomes explicitly resolved. The land is special in that as you get to higher and higher resolution, the demands on the parameterizations increases. More processes become important and we have to parameterize more. That's going to put an immense challenge on the land surface community. But the good news is all the other problems in the atmosphere and ocean become simpler. So there should be more resources for us. Ultimately, at least in my view, we have to move to what Randall Costa worked on years ago, which is actually moving to catchments as our unit of modeling, where we can actually couple the energy, water, and carbon together in a physically sensible unit, a catchment. I don't have a strategy to get us to there. It took Randall Costa a lot of time working with some really smart people to get that working. But I think we need a strategy or pathway to get us to that point as we begin over the years to move to kilometers of global models. Thank you.